Okay, a very welcome to all of you, and I hope everybody is fine. I had thought today I'll not go for any class because of traffic rules. So we will be talking about integral quantum Hall effect, and I think we have developed a basic framework. We have tried to develop the basic argument about the experimental results that were obtained by von Clising in 1980. So you were telling me something. What was that? You were saying, yeah.
How does the magnetic field affect the materiality of a superconductor?
Superconductor. So see, the first important thing is that what is a superconductor? Okay, a superconductor is a material basically. It was discovered by Kamerlingh Onnes in 1900. It was 1913. I'm not sure about the date. And actually, he was performing an experiment on resistivity of metals. Okay, and the metal that he chose was mercury. And it was the time of where people had gained a very good control on low temperature physics. So you could go to very, very low temperatures. So he was performing an experiment and he was expecting the resistivity, how the resistivity will behave when you will take your system to a temperature close to liquid helium temperature. Now, what is liquid helium temperature? It is 4.2 Kelvin, okay? So very, very low temperature. So while performing this experiment, this man got a surprise. And what was that surprise? The surprise was that he failed to measure the DC resistivity of mercury. Even though there was some measurable AC resistivity, but he failed to measure it. So failing to measure the resistivity to a very, very sensitive level indicates that the material is losing resistivity. So if a material loses its resistivity, it has infinite conductivity.
Yes.
So anything that will go in this material in the form of current, it can go undissipated. It can go without any loss for long periods of time. So the point here is that mercury is a metal, okay? And what's the difference here? The difference is that you are taking your metal to a very, very low temperature, right? So when you take it to a very, very low temperature, there is a phase transition. There's a transition, and the transition is from metallic nature to superconducting nature. Okay? Now, once you discover a material, it has to have some of the fundamental properties. Now, how would I call a superconductor as a superconductor? It's based on three arguments. The first argument is resistivity, immeasurable resistivity. Okay? So immeasurable resistivity, it will support your material is a superconductor. But there is another important argument for your material to be superconductor, because you can have other materials where you can find immeasurable resistivity, which is a true case with integral quantum Hall effect as well. So here you have another important argument, and that is Meissner's effect. Now, what is Meissner's effect? The Meissner's effect tells us that the superconductor that you have, it has magnetism, and that magnetism is purely what? Diamagnetic in nature, right? So how do you take, if I call any material as diamagnetic, how do you understand it? You take the sample, you apply the magnetic field, and that sample is going to repel your external magnetic field. Okay, so a superconductor is a superconductor if it follows Meissner effect. That means you apply the magnetic field and it will not allow the magnetic lines of force to penetrate the material. Okay, so if it doesn't allow it, it's fine. Okay, so if you want to kill the superconductivity of your material, what you need to do is you have to apply a magnetic field greater than that of some minimum magnetic field, what's called as critical magnetic field. Okay, so what you do, you apply the magnetic field. The moment you cross the critical point of magnetic field, the material will lose its superconductivity because it will allow the magnetic lines of force to penetrate through. Okay, so point one is here becoming what? The loss of resistivity. But here is another important argument, that is the loss of diamagnetism. Okay, so if somebody tells me what can I say is a superconductor, we call them conventional superconductors. Okay, because nowadays we have high temperature superconductors. Okay, so identification number one is what? Loss of resistivity. Identification number two is Meissner effect, and the identification number three is the structure. Okay, these three things make up a superconductor. If any material does not fulfill these three properties, you cannot call it a superconductor. Are you getting my point? In the similar fashion, you have temperature. Okay, so if your material is becoming superconductor at 4.2 Kelvin, so you have to keep your material below that temperature, because within that temperature range it will act as a superconductor, right? But the moment you will cross that temperature, your material is going to lose the superconductivity, and that temperature is called as critical temperature. Okay, so this is what I can tell you at this stage about the superconductors, these conventional types of superconductors, and we have a complete explanation of these conventional superconductors, what's called as the three people who got the Nobel Prize to giving you a theoretical framework. We call this Bardeen, Cooper, and Schreiber's theory of superconductivity. This theory is valid only for conventional superconductors. This theory cannot explain the superconductivity of high temperature superconductors. Okay, so high temperature superconductors, they can be alloys, they can be compounds, they can be insulators. You can take an insulator from a state of insulation to a state of superconductivity, right? So that's the point. So now going back to our discussion, we have to talk about this very important experiment, integral quantum Hall effect. Okay, we are already aware about the original Hall effect that was discovered 100 years before the discovery of integral quantum Hall effect. It was Edwin Hall who discovered that transverse voltage across a sample, what we call as Hall voltage. Now, integral quantum Hall effect has the three basic requirements. As you know, the story is in front of you. You chomp the electrons between the two semiconductors. Okay, you achieve a thin film, you achieve a two-dimensional gas of electrons, and you perform the Hall-like experiment. But you perform this experiment at a temperature which is very, very close to absolute zero. So this is the first condition, that you are not performing this experiment at an ordinary temperature. You are performing this experiment at very, very low temperatures. And at the same point of time, you make use of a very, very strong magnetic field. Okay? So you apply a very strong magnetic field. That field ranges from 5 to 30 Teslas. So you are using a very strong magnetic field perpendicular to the plane of this two-dimensional electron gas, what we also call as Fermi gas, right? And the next important point about the integral quantum Hall effect is that the imperfections in your sample, they become the guidance for the quantum mechanical Hall effect. They play a role basically. If I have to cut short it, I will tell you that you will not be able to obtain integral quantum Hall effect results in a pure semiconductor. Pure semiconductor, you take pure semiconductor 1, pure semiconductor 2. First of all, you cannot achieve a two-dimensional gas. So impurity and imperfections, which we avoid when we have to create technologies, they play an important role, because what we obtain here is, experimentally, is we obtain resistivity, and we find that this resistivity is independent of the geometry of the sample. It is independent of the imperfection. It's independent of the dopants. It is purely dependent on the fundamental constants of the universe. It's dependent on the Planck's constant. It's dependent on the charge of electron. So let us first plot the results of this experiment, right? The experiment that was conducted on this two-dimensional electron gas. So in a roughly fashion, I would like to draw it, then we would like to have some discussions on it. So what we have, we obtain, so this is my resistivity. Now you can have two types of resistivities, okay? If you have a sample, okay, you have a sample, a two-dimensional sample, you will have a three-dimensional sample. What you have actually is, you have a resistivity along x. I will call that as rho xx, and you have a resistivity along x and y. And this rho x of y is your transverse resistivity. So what you obtain here is, you obtain rho xx. This rho xx is also called as longitudinal resistivity. Longitudinal resistivity. Or it is also called as magnetoresistance. Magnetoresistance. Then another parameter, which is rho xy, this is called as transverse resistivity. Or you can also call it resistance, because yesterday I told you that in a framework I may use the word resistance or resistivity. They have barely a geometrical dependence. I can take the two quantities as equivalent to each other, right? So what you have the transverse resistance, you have the longitudinal resistance. The longitudinal resistance is also called as magnetoresistance, and transverse resistance is called as Hall resistance or resistivity. The choice is yours, doesn't matter. Okay, so what you have a sample, okay? You apply a magnetic field perpendicular to that sample. Applying the magnetic field perpendicular to the sample leads to something that we can write down mathematically as, we call it Landau gauge. We'll be talking about it as we proceed on, but for the time being, this is the nomenclature of the resistivity that we obtain in this experiment. So what is happening? So what is happening? What you are getting is, so this is your, if I choose this as magnetic field, now your magnetic field is not weak, it's very strong. This magnetic field is between 5 to 30 Tesla. And here you have resistivity, and you are measuring two types of resistances. One is rho XX and another is rho XY. Right?
Yes.
These are the two things that you are measuring. You know with what things you measure it, okay? You have the measuring instruments. You perform an experiment in the laboratory. You go back to that low temperature, okay? You go back to that low temperature, you apply a very, very strong magnetic field. When you do all of these things, you obtain a behavior like this. Now this behavior is very surprising. So along this, what I have the resistivity. You can see these plateaus, okay? Plateau 1, plateau 2, plateau 3. They are giving you the measurement of rho XY. Okay? And this I will call as K equal to level 2. This I will call, say, K equal to level 3. This I will call K equal to level 4. All of these plateaus give you the measure of resistivity. And you can see that there is no change in resistivity. Okay?
Yes.
There is no change, and you are changing the magnetic field. Are you getting my point?
Yes, sir.
You are changing the magnetic field. There is no change in the resistivity. And when you measure this resistivity, this rho XY comes in the units of K H by E square. Oh, this is so beautiful. It's something that you are taking from those ideal atomic systems, the ideal systems in which you have a particle in an ideal box. You are taking that quantum mechanics to a system where you have large number of particles, and you are seeing a new thing. You are seeing quantization. You are seeing what we call as Landau levels. The energy. You have a set of electrons with level 1. You have a set of electrons with level 2. This all is happening in the framework of what? It is happening to this two-dimensional gas at low temperature and very, very large magnetic field. And you have those Landau levels. And what is this plateau? What is it? It's resistivity. It's resistance. So resistance is quantized. Now you have to add, you can add resistance to the standard units. The international standard units. In the international standard units, you can use resistance as a basic unit. And if this K equals 2, you are here. If this K equals 3, 4, and 5. But in every case, this K is merely a number. Here you have a number multiple of h by e squared. You have a number multiple of h by e squared. You have a number multiple of h by e squared. And if we take this number equal to 1. If we take this number equal to 1, what will be rho xy? It will be h by e square, and this comes roughly equal to 25.8 kilo ohms. It's a constant. The constant value of resistance, rho xy, 25.8 kilo ohms. And it is also called as Klizzing constant, because this experiment was performed by von Klizzing. So Klizzing constant is what? It is h by e. H by e squared, isn't it?
Yes.
So here is the thing. So if I move on a little bit, what we have here, we have these plateaus, and for these plateaus, we have resistivity rho xy, that is k h by e squared, where this k are merely the numbers. And each plateau, now you have plateaus, at each plateaus, you have a magnetic field. You have a magnetic field. And that magnetic field is h by e n by k. While this h by e is called quantum of flux. We call it quantum of flux, phi naught. So when the quantized packets of magnetic field are trapped, you are obtaining those plateaus. You are obtaining those Landau levels, right? So till now we talked about rho xy. Now let's go back to that graph. Let's go back to this graph. This is your story. And now what we see is something like this. I'm making a bad diagram, but I hope you'll get the idea. Now this graph that I have plotted here, I should have chosen a different color. Okay? Now this graph that I have plotted here, what do you see in this graph? You see the resistivity is 0. Okay?
Yes, sir.
And once you reach the plateau, once there is a jump, there is a peak. Now this, another graph that I have shown you is representative of rho x-axis. Okay? So what do you observe from rho x-axis? You observe there is no resistivity along x, and then there is a sharp transition. So no resistivity means what? Your sample is in this direction, it's a conductor. Okay? It's a perfect conductor. But once you reach at the edge of the plateau, there is a peak. That means resistivity has a sharp increase. So what is happening? Your material is behaving like an insulator. Okay? Right? Then you move on, what's happening? Again, you have zero resistivity. Okay? So your material is behaving like a perfect. No, don't call it a super, because there are other things going on.
Yes, yes.
Okay? So don't try to mix the things here. It will become confusing. So I'm calling it perfect conductor because resistivity is very, very less,
Yes.
almost 0. And I'm calling it a perfect insulator the moment it reaches the edge of that plateau. And you are repeatedly see this kind of nature, right? Okay? So what's happening here? You have continuous transitions of the material. Your material is a conductor, again it's an insulator, conductor, insulator, conductor. So there is a phase transition going on along the x-axis, right? And we can at least have an idea about this argument using the classical approach, right? So in the classical physics, we have a very popular model, what we call as drug model. We can use drug model here to at least realize certain things, and then we can move on further from there. Okay, so can I rub this?
Yes.
Okay, so I don't have to rub it, I can move on. Okay, so I will treat this experiment for the time being as a three-dimensional problem. Okay, so when you have a problem like that, what I can say here is the very fundamental law of solids, the very fundamental law of metals, what we call as drug law. And what you have Ohm's law, V is equal to IR, right? You know everything about it. Okay, let me make it a more reliable kind of law. If I write down V by D equals I by A R by D. Can I do like this? So this is your, I have divided by D, I have divided by D, they will cancel. I'm multiplied by A, they'll cancel. And this is what? This is electric field, okay? So we are doing pure classical physics. This is electric field is equal to, what is this? Current by area. This is current density. This is J. And this is A, and then, what is this R? Okay, this is R, this is D. Okay, I think you know R is equal to rho L by A. Okay, so can I get anything from here? So what is rho? Rho is AR by L. This is it?
Yes, sir.
So this thing is rho, isn't it?
Yes, sir.
So what is J?
Current density.
J is E by rho. J is E by rho. But rho is the reciprocal of sigma, because sigma is called conductivity. Right?
Yes, sir.
So what you have a relation between current density and conductivity and the electric field. Okay? I obtained this equation from Ohm's law. So this is Ohm's law that is in front of you on the board. J equals sigma E. Now, as long as the electric field is in the same direction of current density, this sigma is a simple number. What is it? It's a simple number, it's a constant, right? But if your electric field has components, if your electric field has,
Components.
it is a tensor. This sigma is a tensor. It's a 2 by 2 matrix. So sigma is a tensor. It's a 2 by 2 matrix. It's a tensor. It's a 2 by 2 matrix. So I can write down this sigma as a matrix of, I can write it as a tensor of sigma xx, sigma xy, sigma x, I will write xy, in fact it should be yx, but I will keep a negative sign here. And then you will have sigma yy. And these are the components of the conductivity that you have. And you are writing them in the form of a tensor. Okay? So sigma is tensor. Once you are in a two-dimensional plane. Isn't it?
Yes.
Are you getting it? So corresponding to sigma, you will have rho. Sigma is the conductivity, rho is resistivity. So what will be rho? Because rho is 1 by sigma. So what will you have? You will have rho equals a tensor of rho xx, rho xy minus rho xy and rho yy. Now see, these elements are the symmetric diagonal elements of this tensor. Okay? Rho xx and rho yy, these are the symmetric diagonal elements of this tensor, and these two elements are anti-symmetric diagonal elements of this tensor. Right?
Yes, sir.
Are you getting it? Now, you can do simple mathematical manipulations and you can obtain the relations between sigmas and rhos. I mean, you can get the relation between the components of sigma and the components of rho. So what you will obtain, when you will do these manipulations, what you will obtain is, I would directly write down the result, that will be rho x, no, I'll write it in terms of sigma. It will be sigma xx will be equal to rho xx divided by rho xx square plus rho xy square, comma, sigma xy will be equal to rho xy by rho xx square plus rho xy square. Okay? This thing is basically used here to understand that peculiar nature that you have, that your system has, it is a perfect conductor, then it's a perfect insulator. Okay, now see, if I tell you that, if I choose rho xx, if I choose this value equal to 0, what will you obtain from here? If rho xx is 0, sigma xx is immediately 0. Isn't it?
Yes, sir.
Sigma xx is 0. What I have chosen?
Rho xx.
Rho xx.
And sigma, yeah, okay?
Definitely.
And what about sigma xy? This thing will be 0?
Yes, sir.
Here you will have a cancellation of rho xy and square. So what will happen here? You will have sigma xy equal to 1 by, it has to be minus here, okay? It will be minus. So you will have minus 1 by rho xy. This is quite normal, nothing wrong with it, okay? So I chose rho xx equal to 0. I will have sigma xx equal to 0. And sigma xy will be
Minus 1.
simply minus. Okay, minus is giving you the direction. Okay, is this clear?
Yes, sir.
So what is happening here? I chose rho xx equal to 0. Now if I choose rho xy equal to 0,
Second one is 1.
if I choose rho xy equal to 0, then sigma xy will be 0 and sigma xx will be,
1.
forget about that also. Okay? So the two things that we have, rho xx and rho xy. So, if this rho xx kind of thing is here. Rho xx equals 0. So this is 0. And this is quite normal. And rho xy is equal to 0. What do we obtain? In that case, if this is 0,
Then this is 0.
this thing is 0, and
1 by rho x.
this will be 1 by rho.
Rho xy.
Okay, that's fine. Look at this result. I was looking for this result. And tell me about this result. I want you to talk about it. What is that? Tell me. Sigma xx equals 0 and rho xx. Is it rho xx? Yeah, rho xx equals 0. Come on. See, can you translate it into your language? What does it mean? It means
Conductivity
conductivity is
0.
0. Conductivity is where 0? When you will say conductivity is 0? In a conventional sense, you will say, sir, it is an insulator.
Yes.
Because you are saying that conductivity is 0. Right? But in the same framework, rho xx is 0. So rho xx 0 means 0 resistance. Right?
Yes.
So that means here you expect it to be a perfect insulator. See how tensors help us realize things in simple sense. And here you have a perfect conductor. And I think we will stop here. Okay? Okay? We'll stop here, and when we'll next meet, we will talk ahead of it. Okay? Any questions? Okay. Thank you. Bye.